Hello everyone. So today we'll talk about exercise 8.35, fractal triangle. So in this problem we're trying to find the moment of inertia of a fractal triangle. So what exactly is a fractal triangle? Well, we start with an equilateral triangle with side length L, and then we remove the middle equilateral triangle, formed by connecting the midpoints of each side. So we remove this part. And then we continue this process indefinitely. So we remove here. We remove here, and then we remove that. And then here are more triangles, so we continue to remove each triangle. And then finally, the shape that we get finally is called a fractal triangle. And so we are just trying to find the moment of inertia of this fractal triangle. And specifically, we want to find the moment of inertia of this shape about a line that goes from the top vertex straight down to the middle of the opposite side and going through the center. So this is hard because this shape is very complicated. It isn't really realistic to just integrate uh, each small part. So let's try to identify a pattern since these shapes are all self-similar. What does that mean? Well, that means each shape is quite has the same structure. So isn't it true that this big triangle is in no way different from this triangle, other than that their mass and the length is different? Their structures are fundamentally the same. And so this makes us think that maybe we can try to find the moment of inertia of these smaller triangles first, and then add them up to get the final big triangle. So let's first define the quantity that we want to find, which is the moment of inertia of the full fractal triangle. So let's define that quantity to be I, center, L. So center just means that we're finding the moment of inertia through an axis around an axis that goes through its center. And then L just means is the outermost, the boundary is an equilateral triangle with side length L. So this is the moment of inertia that we're trying to find. And then what is it made up of? It's made up of three more smaller triangles here. And these are also fractal triangles that share exactly the same structure as the big fractal triangle, except that their mass is smaller and their side length is half L. And then we can ignore this part since it's empty. So let's try to define moment of inertia for these three triangles too. So this one and this one is the same because uh, they they are all the moment of inertia around the vertex. So let's define that quantity to be I vertex half L over 2. So this just means that we're finding, so that this quantity just means that it is the moment of inertia of a fractal triangle around of length of side length L over 2 rotating around one of its vertex. So this is I vertex L over 2. And then what about this triangle? This triangle is a bit different because look at this line here. It's rotating around around an axis that's going through its vertex to the middle point of the opposite side. And it's basically similar to the large triangle, so we also call it I center, except that is L over 2 now. So just to make this clear, this corresponds to this and that. And then this quantity corresponds to this triangle here. And then so the final expression should be I center L equals to I center L over 2 plus 2 times I vertex L over 2. So this is basically saying the the total moment of inertia of this fractal triangle of side length L equals to the contribution from these two smaller triangles and the contribution from this other triangle. So this is the formula that we're trying to use. And then now let's look, we have two unknowns. That means we need two equations. So we are missing one. And how can we get that missing one? Well, we can obviously write these quantities as we can break as other quantities as well. Like we can break this down. So if we separate this, we can get this, this, and that. But this doesn't really help because this is infinite. Like this continues into infinity, and this process never stops. So we need some sort of equation that is different of this form. So where can we get that second equation? Well, we can use a scaling idea since we know that, so basically the idea is that we know that moment of inertia depends on m and L. So to make it more clear, we know that I equals to the integral of r squared dm. So we know that I is scalable. So it is basically, it depends on the mass and the distance squared. So it depends on these two quantities. And so then we can write a scaling, an equation that equates this with this and then this with that using the scaling idea. So how can we do that? Well, first, let's try to compare the full fractal triangle of side length L with a smaller one of side length L over 2. The full triangle has 3 times the mass of one small triangle. So this large triangle that we're trying to find, or this fractal triangle, the mass of this large one equals to 3 times the smaller one. Why? Because we divide them into 3 parts. So this part, and this part. So the larger, or to put it this way, the mass of this equals to 3 times the smaller one. So now we know that the full triangle is 3 times the mass of the small triangle because it is made up of 3 small copies. And then we know that all distance are 2 times as large in the full triangle. And so since we said moment of inertia depends on m and L squared, we know that this gives a factor of 2 squared equals to 4. And so that the total scaling factor is is the factor for mass times the factor for L squared, which is 3 times 4 equals to 12. So again, to make this more clear, since I only depends on the mass and L squared, and since in all formulas the formula is of the form alpha m L squared, so this alpha is some coefficient, some constant coefficient, and this they multiply, and this is why we can do 3 times 4 equals to 12. So if m scales by 3 in this case, and L scales by 2, then this quantity as a whole scales by 12. And then this alpha, this constant coefficient, is the same for both the fractal triangle big one and the small fractal triangle, since they are the same structure, they are self-similar. And so now we know that I center L equals to 12 I center L over 2. So here we're just getting a relationship for the center L over 2, since if you do the vertex, so we will have to use the parallel axes theorem. And so now we need a formula for the I vertex L over 2. And here we will use the parallel axes theorem. And it says that if we move the axes that the object rotates around sideways, the new moment of inertia equals to the old one plus md squared, where d is the distance moved. And so now let's try to utilize this parallel axis theorem. So let's draw out the triangle here, and then we carve out a smaller one in the middle. So imagine these are all smaller fractal triangles, and they are all side length L. Remember previously that the relation I center L equals to 12 I center L over 2. This only applies to the center triangle. So it only applies to here, this triangle right here. And so how can we use the parallel axis theorem to find the moment of inertia of these two smaller triangles? So let's first look at where it's rotating. So it's rotating from here. And then how much has it moved? Well, we know that it has moved. So this is the center here. But this center is equivalent to us just using this point because it is moving sideways, not up and down. So up and down doesn't really matter. So we're just moving sideways. So how much have we moved? So what is the distance here? It is half of this side length, half L, right? So it's just 1 over 4 L. And so we know that D equals to a quarter L. And so now we know that I vertex L over 2 equals to I center L over 2 plus M over 3 times the distance moved, which is L over 4 squared. And so now let's try to put everything together. We knew that I center L equals to I center L over 2 plus 2 I vertex L over 2. And so I center L over 2, I center L plus 2 I center L over 2 plus M over 3 L over 4 squared. And so now let's try to simplify this. We get I center L over 2 plus 2 I center L over 2 plus 2 times ml squared over 16 times 3, which is 48. And so we have I center L equals to I center L over 2 plus 2I, or we can combine these, so we get 3I center L over 2 plus ml squared over 24. And so now let's use our previous relation, the relation that we got previously using the scaling law here. So we have now, so we know that I center L equals to 12 I center L over 2. And so 12 I center L over 2 equals to 3 I center L over 2 equals to plus m L squared over 24. And so this is 9 I center L over 2 equals to ml squared over 24. And so I center L over 2 equals to ml squared over 24 times 9. 216. And then we're trying to find I center L, remember. And this is equals to 12 I center L over 2. And so it's 12 ml squared over 216. And that is and that is 1 over 18 ml squared. And that is the moment of inertia of a fractal triangle, fractal equilateral triangle of side length L. And that is also our answer to this question. Thank you for watching.